We're going to look at a couple of limits here, starting with the limit as x approaches 2 from the minus side of the log base 5 of the quantity of 8x minus x to the fourth. One approach here would be to factor the argument of the log and use a property of logarithms. So I'm going to write this as the limit as x approaches 2 from the minus side of the log base 5 of x plus the log base 5 of the quantity of 8 minus x cubed. So that's factoring the x out of the argument. X times the quantity of 8 minus x cubed is a product, and so we can write that as a sum of logs. As x approaches 2 from the minus side for the log base 5 of x, we can simply write the log base 5 of 2. For the second log, though, if we put 2 in place of x, we have log base 5 of 0, and that's not defined. Remember that the domain of a logarithmic expression is from 0 to infinity. However, it is the case that as x approaches 2 from the minus side, 8 minus x cubed approaches 0 from the positive side. See, we're talking about approaching 2 from using values less than 2, and so cubing them will give us values less than 8. And looking at the graph of a logarithm that has a base larger than 1, if the argument approaches 0 from the positive side, then the function is approaching negative infinity. So our answer here would be log base 5 of 2 minus infinity. The answer to the limit expression is that it becomes negative infinity. I had said that that was one approach. The other approach would have been to analyze directly as x approaches 2 from the minus side what happens with 8x minus x to the fourth, and seeing that it would be negative, but I think it was a little clearer when we split it up into two factors. Next up, the limit as x approaches infinity of the quantity of natural log of quantity x plus 2 minus natural log of quantity 1 plus x. If we picture the graph of a logarithmic function with a base larger than 1, which we have now because we're looking at natural log, base is e, and I really should put arrows on my graph. I'm going to go back to the last one. Just little details like this are important in math. Okay, as x approaches infinity, we can see that the natural log has a limit of infinity. Therefore, if I were to try to directly substitute infinity in place of x, we would actually end up with infinity minus infinity. And we might think that that's 0, and sometimes it is, but sometimes it's not. We're going to see that in a later section. Infinity minus infinity tells us we need to use a different approach. And in this case, that approach is going to be to use a property of logarithms again. So we're going to write this as the limit as x approaches infinity of the natural log of x plus 2 divided by 1 plus x, writing the difference of logs as a quotient inside the logarithm. Now you may recall from an earlier chapter in first semester calculus, as x approaches infinity, x plus 2 over 1 plus x, well, to compute that, we can divide out the largest power of x that appears in the denominator, and we end up with 1 plus 2 over x divided by 1 over x plus 1. And as x approaches infinity, the terms that have an x in the denominator go to 0. And so, give myself a little more room there, this expression approaches 1. In other words, the limit as x approaches infinity of x plus 2 over 1 plus x is equal to 1. So together with this property of logs, we're going to use a property of limits that says that a limit can essentially pass through a continuous function, in this case that being the natural log. So this becomes the natural log of the limit as x approaches infinity of x plus 2 over 1 plus x, which then becomes the natural log of 1, replacing the limit expression with what we know its value is. looking again at our graph, if the input is 1, the output is 0 for y equals the natural log of x. Therefore, this limit is 0, and it turns out that today, infinity minus infinity is equal to 0. Keep in mind that's not always the case.